Pranatila, welcome to this last session of our course Mechanical Vibrations, and today we are going to discuss about vibration in beams. And in the last lecture we discussed about the vibration in strings. Both are cases of continuous vibration, but we study these two different natures of continuous vibration. And the reason is, uh, if you remember, in the strings, what you call vibration in strings, when there was a vibration, the restoring force was tension. Restoring force was tension. There was no stiffness involved. There was it was a single one-dimensional geometry. There is no breadth and width. Sorry, so there is no stiffness that was involved in the calculation. The motion of wave was small and transverse in nature. So because of that, the response, or you can say the frequency of vibration, depends on tension. And for the harmonics, and just as we have calculated last time, are simply an integral multiple. It was n lambda and pi. So and wave, there's a clean propagation of waves and so on and so forth. So common examples are the vibration in the strings of any musical instrument, or even the electrical wiring. It can be also classified as a string, and then you can perform the vibration analysis using the continuous vibration theory. So unlike these strings, the vibration in bars is, the fundamentals are same, but the nature is different. Vibration in bar, or you will sometimes find vibration in beams, or somewhere you will see them classifying it as vibration in rods. So in the vibration of bar, beams, or rod, the restoring force, because now we have a 3D geometry, so the restoring force is actually the stiffness of the material. The restoring is because of the elastic stiffness, or Young's modulus. And it does has some rigidity, bending rigidity. It opposes the deformation, it resists the deformation, and we call internal stress that resists deformation. And it can have a different kind of vibration, not just longitudinal. It can have a longitudinal, it can have transverse, or bending, or torsional vibration, you can say. So it can have different modes of vibration in the case of bars or beams. So owing to this, the nature of vibration, let's say called frequency of vibration, depends on material stiffness in geometry, not just tension in the rod. Depends on material stiffness in geometry. So now it is more realistic. It takes into account the whole geometric and the material properties into account before calculating its response. And it is strongly dependent on the boundary conditions. So they do have a significant impact on the type of the response a system may exhibit if it is subjected to an excitation force. So that was just a brief introduction why we are studying two different kinds of continuous vibration, two different sections of continuous vibration, why it is necessary to study them. So now we'll start with the longitudinal vibration in the beams. So let's suppose you have an elastic beam with varying cross-sectional area. So you can draw any of the elastic beam with a different cross-sectional area. I'm not making it smooth, so it's like this one. And so the total length of that beam is, you can classify as L. And now we are trying to observe, the vibration in this small section. So let's say this position is X and this is dx, and let's call it A, and that's this point as B, this point as C, this point as D. And so now once any external force is applied, so the force will be acting along the cross section of this beam, right? When there's some pressure applied on this cross sectional area, so it will be applied across the cross section. So if we just take out this section and draw it separately, so it will be like this ABCD. So originally it was like this one, that was original one. So let's say the pressure was being applied, a pressure was being applied in this direction, and the resultant position at this point would be P plus dP, that is this change across this thickness of dx. And now because of this external pressure, there's some elongation in the beam longitudinally. So let's draw the elongated section, or displaced position you can say. So now we have, previous one positions were A, B, C, D. Now our new positions are A prime, and then we have B prime and C prime and D prime. So these are our new positions. Now it has moved from, let's say this was a displacement U, and this was U plus du. So if we try to write down the equation of motion for this vibration beams, so first of all you have to classify what the pressure, how we have to define the pressure here. So we know the pressure originally is equals to stress into the area, and the stress is equals to Young's modulus. Come on. The stress originally is equals to Young's modulus into the strain, that is partial U over partial X. That's a change, that's kind of strain in the beam U. So the strain elongation in the beam with respect to position X, to partial U over partial X into the area. So now that's our new pressure equation, or you can write it as E A partial U over partial X. So just remember this expression. I will write it nicely. So now based on this, we are going to write the equation of motion for our system. So the total force that is being acting onto our section is the force that is externally being applied. You can call it F across this section dx, and let's say the force is being applied here, and then based on that there's internal pressure being generated across the cross section of the beam, and as a result it has some inertia. So we can classify as, so we have, let's all towards right side is positive, so we have P plus dP plus F dx minus P, because that was on the other side. This whole equal to the inertia of the system, and inertia of the system is equal to basically ma, and m is equals to, if you write ma, it is equal to density into the volume and into the acceleration. So we have density A, and that will we have volume. Partial u over partial t square, that's an acceleration. So the next would be, we can simplify it further based on the expression we found for the pressure, and for dP is actually equals to change in the pressure with respect to x into dx, because we are observing, we know that the pressure is not totally dependent on the position. It has some other influences as well, so that is partial differential for this one. So you can write it as, if you substitute that pressure equation and then this one into our original equation, it will become partial over partial x, and that pressure would be equals to EA x partial u over partial t, and u is dependent on x and t. That is partial u over partial t plus f xt, and that's density x a x into the acceleration partial square over partial t square of u xt. So for a uniform equation, for a uniform bar, it will become equals to a bar with uniform cross section. It becomes EA partial square u over partial x square xt plus f of xt equals to partial, come on, I apologize because I'm trying to use a different mode on my device, so it helps me to write comfortably accept this issue. So that becomes equals to, yeah, density into the area into the acceleration. So you see, we are going toward the similar pattern like we did in the vibration strings. So we are moving towards what you call the wave equation. Since we are trying to analyze free vibration, for free vibration f xt would be equals to 0. There's no external force being applied, so whole equation will be reduced to E A, and that's become partial u partial square by partial t square of u xt equals to double partial derivative of uh, sorry u xt, that is with respect to x not t. So we are reduced to this equation. Now we can simplify it even further, so it will become E A over, we had two more, into density into area, and that is partial double derivative of u with respect to x and t, and then we have double derivative of u xt with respect to time. So this cancel out and we are left with E over A, and let's call that C equals to under root E over the density, elastic modulus over the density, and that tells us about the speed of sound in that medium. In the material. So we can write it as c square partial double derivative of u with respect to x into partial derivative of u with respect to t. So that's again about this famous wave equation. And if you recall, we tried to solve that one in our last lecture using a special method for the partial differential equation. So that's the same equation we have here in the vibrational strings. So we use a separation of variable method, and then we solve them separately. We tried to we separated them all the differentiation with respect to the position and all the differentiation with respect to the time, and at the end we have an equation. We reached an equation where u was equals to this and t was equals to this. So we can directly plug out this equation and substitute that one in our solution. So again, using the separation, I'm not going to perform the whole all those steps because they're the same steps. So I will just write using separation of variable method for PDE, partial differential equation. So we know u, just write it nicely, u x t is equals to u of x and t of t, and if you solve them, so you will have at the end equals to the same solution as we have calculated last time, a cos omega x over c plus b sine omega x over c into c cosine omega t plus d sine omega t. That's a general solution of our vibration, longitudinal vibration in the bars or the beams or the rod, whatever you like to say it, call it. So that's the general solution of our system. So this is the solution. Now how you can find out a, b, c, d, you have to use the initial and boundary condition for a, b, c, d like we did before. For a, b, c, d, use initial condition and boundary condition. So if you just check out, now you have a homework to do yourself, just for yourself to practice. In your book you will find this table. So they have given solutions for different boundary conditions. So let's say if your bar is fixed and free, so it means it's at the zero position. At the zero position, this is 0 and this is the full length L. That's the whole length L. So at zero position the displacement will be 0 at all times t. Maybe it's t is equal to 0 to t is equal to infinite. It will be 0 all the time because it is fixed. And the change with respect to the position of L and T is equal to 0. So the change